or maybe the most common sugar, and we're going to draw it in a chair conformation. And the sugar that I'm drawing here is glucose. And it's kind of easy. I like it because when I draw my chair like so, all of the substituents are in the equatorial position, so it's very easy to remember the structure of glucose. Now, sugars have an aldehyde group, and we're going to talk more in a second, but for the most part they exist as cyclic hemiacetals. And I'm going to draw, we have another stereocenter for a cyclic hemiacetal, and I'm going to draw that hydroxy group at this position, at the 1 position that we'll learn is called the anomeric position. I'll draw it equatorial. This molecule is called beta-D-glucose. And so it's a member of the class of carbohydrates. I guess if you go to the gym, you might call them carbs, of course. It's a nickname. Its molecular formula is C6H12O6. And if you think about it, then the reason it gets its name as a carbohydrate is that the formula is carbon plus H2O. And literally, if I take some sugar, if I take some table sugar, and I take sulfuric acid, which is very dehydrating and can yank all the water out and carry out a whole bunch of reactions. If you've ever seen this done, you just put it in a beaker, put some sugar in a beaker, pour on some consulfuric acid, and this big snake of carbon comes out of the beaker, this big rod of frothy carbon and sulfuric acid along with a little bit of smoke and so forth. Anyway, I'm not going to do that demonstration here, in part because it's kind of hazardous, but it's a lot of fun. So glucose is a member of a class of carbohydrates, a broad class of carbohydrates that we call aldoses. And the reason we call it an aldose is that when we go ahead and unwrap the structure, when we break up the hemiacetal at the 1 carbon, you get an aldehyde. There are also sugars where if you break up the hemiacetal, you get a ketone, and those are called ketoses. We'll talk about those later. Glucose is a 6-carbon sugar. We number it from this position 1, 2, 3, 4, 5, 6. And so glucose is called an aldohexose. Hex is 6. And I guess to be consistent, I will write an aldose to indicate it's one of many. There are a bunch of other things get called. Because glucose has a 6-membered ring containing an oxygen in the closed form, in the hemiacetal form, we call it a pyranose sugar. Pyran is a 6-membered ring containing an oxygen atom. Tetrahydropyran is a saturated 6-membered ring containing an oxygen atom. So glucose is a derivative of tetrahydropyran, so we call it a pyranose. The other important ring containing oxygen is a 5-membered ring containing an oxygen. The aromatic compound with double bonds in it is called furan, and if you have all hydrogens on the ring, if the ring is fully saturated, you call it tetrahydrofuran. Tetrahydrofuran, we've seen that THF is the solvent, and so there are other sugars that have 5-membered rings in them that you would call a furanose or a furanose form of the sugar. And I guess as long as we're talking about names here, we would also refer to glucose as a monosaccharide. Mono, of course, means one. Saccharide, well, sugar. I want to give us some contrasts in structure and in stereochemistry by drawing a disaccharide at this point. And it's going to introduce some basic concepts here. So we're going to start with drawing another pyranose form of a ring. We're going to have two of these linked together, so two chair cyclohexanes. And I'm going to go ahead and draw everything the same on this ring as I did for glucose, except at the 4 position, I'm going to, instead of having the hydroxy group in the equatorial position, I'll put the hydroxy group in the axial position. And we're going to make a molecule with 2 sugars in it. It's one that you might have consumed this morning, one that actually is good for you. Well, maybe, I guess all sugars are okay in moderation. Okay, so we're going to link to another ring here. And this ring will have, as a glucose type ring, like so. So here's our disaccharide. Disaccharide is lactose. I guess my drawing isn't the prettiest in the world. I'm always delighted when I look at people's notebooks and see their drawing so much prettier than mine. So lactose is a disaccharide. And I think there are a couple of interesting take-home messages that we get from this. First of all, sugars can be linked together one to the next to the next. Starch, for example, is a long, long chain of sugars, as is cellulose, basically a polymer of almost infinite length. Now, you might look and say, well, it's a little different looking than glucose. I mean, we've basically formally removed one water molecule. So if you write out the molecular formula of lactose, it's C12H22O11. And so you'd say, well, we don't have the same ratio of carbon to hydrogen as we had because we've connected in glucose. But if you notice, it's still a carbohydrate. It's still effectively carbon plus H2O. In this case, 12 carbons plus 11 H2Os. In the case of glucose, 6 carbons plus 6 H2Os. So if you look at our lactose, as I said, we have 2 units in it. We have our glucose unit. And now we have another sugar unit in it, and this is a galactose unit. So galactose, let me draw out galactose and glucose in just a second, but I just want to make one last point. We have a linkage from the 1 position of glucose, right? So this is the 1 position, and then to the 1 position, of galactose, and that's the 4 position of glucose, right? We number our way around the ring 1, 2, 3, 4, 5, 6. And so we call this a 1 to 4 glycosidic bond, glycosidic linkage, or glycoside bond. I want to draw out the units, the subunits here in galactose. So I'll draw out the 2 sugar units. I'll redraw glucose again. It pays to practice a little bit in your drawings, and I've got to say I'm no artist as far as cyclohexane rings go. Basically, the theory is you're going to be making parallel lines. So the equatorial bond for this OH group is parallel to the CO bond for this one. The equatorial bond to this OH group is parallel to this one. As I said, I'm not much of an artist, but I can get my ideas across competently. All right, so galactose, so this is glucose, or more specifically beta D-glucose. We'll talk about what that D means in a second. And now we'll draw galactose, more specifically beta D-galactose. I'll talk more about that beta in a second. All right, so everything is the same over here, except as I was indicating when I drew our molecules, now we have a different stereochemistry at the 4 position. So 2 isomers that have the same connectivity, all of the same atoms connected together in the same way, but just differ in the stereochemistry of one position, are diastereomers. They're stereoisomers that are not enantiomers. Remember, when you learned about stereochemistry, you learned about enantiomers, compounds that are non-superimposable mirror images. You learned about diastereoisomers, stereoisomers that are not enantiomers, and then you learned about constitutional isomers, molecules that have different connectivity, different arrangements of atoms. All right, at this point, I want to draw another structure, and I'm deliberately proceeding reasonably slowly and methodically here because I think it really takes some time to bring all these ideas into your head and to dust off the cobwebs on some of the stereochemistry and structure that you learned back in 51A. So I'm going to draw a different structure here. We're going to do everything the same as glucose, with one exception. I'm going to now, instead of having our stereochemistry at the 1 position be equatorial, instead of having the hydroxy group at the 1 position be equatorial, I'm going to have our hydroxy group at the 1 position be axial. Now this is alpha D-glucose. And in the convention of organic chemistry, you have beta as the up position, the top face of the ring. Alpha is the bottom face of the ring. So the OH is pointing down to the bottom face as we've drawn it at what we call the anomeric carbon